moving on to linear mappings. So consider two vector spaces, V and W. Let L be a mapping from V into W. And so remember, functions are mappings. It's kind of like a function from one vector space into another. We call L linear, or say that it's a linear transformation or a linear mapping, when for all U and V in your vector space V and real number C, the following properties hold. First, L of U plus V is L of U plus L of V. Second, L of CU is C times L of U. Something to take note of. This addition here is addition as defined in V. This addition is addition as defined in W. Right, so they're not the same plus operator. Same thing with here. This is scalar multiplication as defined in V, whereas this would be scalar multiplication as defined in W. So not the same scalar multiplication. If L is a linear mapping of V into itself, then we just say that L is a linear operator. And you've actually been working with linear operators. The derivative is a linear operator. The integral is a linear operator. Right, so let L from V to W be a linear transformation, and we're going to say that U and V are vectors in V. L of the zero vector in V will be the zero vector in W. L of negative V, negative L of V. And remember, the negative V is your additive inverse of V. L of U minus V, L of U minus L of V. And if your set of vectors V1 to Vn spans V, then the set of vectors L of V1 through L of Vn spans W. Let A be an m by n matrix for every vector v in Rn. A times v is a linear transformation from Rn into Rn. So we're going to show that this function, f from R2 to R2 that is defined, f of xy equals x plus yx, is a linear transformation. Let's call this a conjecture. Thomas' conjecture was not going to prove it. This is another way that they define a linear transformation. Right, so instead of showing the two properties, you just go alpha v plus beta w is alpha f of v plus beta f of w. So what it does is it shows both properties at once. take two arbitrary vectors in R2 and two arbitrary constants. What we want to do is we want to show that this, f of that linear combination, is the linear combination, so alpha times f of xy plus beta times f of uv. So multiplication and addition in R2. That's what we get, right? Now apply the mapping. Mapping says is take your first component, add it to your second component. That's our new first component. Second component. New second component is just the old first. So that is our transformation. That's the vector we don't have to work with. Here's what I'm going to do. Let's take that first component. Well, that's just addition of real numbers, right? And that is associative and commutative. So order doesn't matter, how we group it doesn't matter. Let's group the two terms with alphas together, two terms with betas together. Can't we write this as the sum of two vectors? Be that somewhere. And the first vector, the first component has an alpha and common factored out. Second vector, you have that beta. Where we go then write this? Right, scalar multiplication, we factor that alpha out of the first vector, factor that beta out of the second vector. Right? Oh. What's this vector? It's the transformation of the vector x1. Then what's this stuff? Isn't that the transformation of the thing? Is that not what we wanted to show? So we're not. It's a linear transformation.
What's that?
Rather than filling in the box, we just put it next to it. I'm assuming you're talking about this.
Yeah.
Yes. Instead of, because normally you use a filled in square to mean QED end of proof.
Oh, okay.
But that kind of is tedious to write, so we've just decided to put it next to the block instead. Still means the same thing, just means QED.
Okay.
End of proof. QED is Latin for something, I forget the phrase. But it means as was to be shown, or something along those lines. The beautiful thing about this one was, right, it was an operator. So it was from R2 into itself. So the operations were exactly the same, so you don't have to really worry about keeping track of those. You ever gone from R3 to R2? No, again, thankfully, the operations are exactly the same. So you don't have to worry about keeping track of those. So two arbitrary vectors in R3. And two arbitrary constants. This one, you know what I might do with this one? I might just try to show both properties individually, because the algebra is going to get really messy if I use the conjecture. This might be one of those cases where it might be better just to do it individually. Do we have enough room? Yeah. So start with the sum. We want to show that transformation of the sum is the sum of the transformations. Well, we're dealing in R3. Vector addition in R3. I just added those. So that's the vector we're now transforming. That's where I said the algebra is going to get hairy. Should be enough. The transformation says, for the first component, it's the sum of the three. Now for that second one. That is what the mapping rules tell us to do, right? Remember, that's another way you can think of function, right? So it's a rule that tells you what to do. Now we have to simplify that. What are we going to do? Well, I guess let's drop the parentheses. So first component, just drop parentheses altogether. Second component, distribute. This is not Y, sorry. X plus W. Then what? 2x plus 2u minus 3y minus 3v plus 4z plus 4w. Like that. And you should be able to see where we're going at this stage. Addition is commutative and associative. So group X, Y, Z together, group U, V, W together. Well, now we can write that as the sum of two vectors, right? What's this vector? Of what? That's just f of x, y, z, right? What's this?
F of UVW.
Which is what we want. Let's not be mathematical. First property shown. That makes me happy. It's finally face. Now we just have to show that second property. Which was to throw in a scalar multiple of a vector into the transformation and show that it's the scalar multiple of the transformation. Well, again, we're dealing in R3 originally. Scalar multiple in R3. Is that, right? Alpha x, alpha y, alpha z. Now apply the transformation. What did the rules say? Going to get a 2 vector. The first component is the sum of the 3 components. Your second component, twice the first, minus 3 times the second, plus 4 times the third. Right? Oh, we can factor in alpha from the first. Factor in alpha from the second. Since we're dealing in R2, we can factor that alpha out of the entire vector. That is f of x, y, z, isn't it? No smiley face there, because that's the second property proven. Therefore, the mapping f from R3 to R2, find by that is linear. QED. So a few additional comments back up to here. This itself is the mapping, right? That's what we're assigning the mapping as. Just like in pre-calculus, right? You say f goes from reals to reals. F is what you're representing your function by. Then you have your rule. Let's go down to here. This is the rule of the mapping, right? It tells you how f is being applied. So it should come as no surprise. V is your domain, W is your range. I'll just look here, right? What you're plugging into the transformation is called your pre-image. What it transforms to is called your image. Right, so L of U would be the image of U. U is your pre-image of the transformation. Right, so that might be some new terminology for you. Image versus pre-image.
Sorry, could you just repeat which one's pre-image and which one's image again?
Pre-image is what you're plugging into it.
No, I mean in terms of value.
Yeah, so U would be the pre-image. It's what's being plugged in. So in terms of functions, the pre-image is your input.
Gotcha. And the output would
The output is the image.
next.
So L of U
Gotcha.
is the image of U under L.
Okay, I just wanted to make sure I'm writing that properly.
Because that terminology does appear in the textbook when dealing with transformations and mappings. After the exam, we do examine the range a little bit more in depth. Right? But obviously the range is just the set of all the images. But we'll examine that a bit more in depth after the exam, as well as what's known as the kernel of the transformation. And we'll see how kernel and range actually relate to something that we just studied. Let M be an arbitrary but fixed matrix in M22. Right, so it's going to be an arbitrarily chosen matrix, but it is fixed throughout the problem. Right? Once you choose it, it stays fixed. It's now your matrix. Right? It'd just be like I say, pick a number. right? You can arbitrarily choose a number, but now you're stuck with that number once you pick it. What was M22 again?
It's the 2x matrix, right?
What about 2 by 2 matrix? M22 is a set.
It's a set of two 1 by 2 matrices. No.
You're on the right track with the 2 by 2 matrix. So maybe this is a hint then. Maybe you want to go through the textbook in the lecture video, list out the notation for all the different vector spaces. M22 is the vector space of 2 by 2 matrices under standard matrix addition and scalar multiplication. Right, there are several notations that were introduced. Remember the P4? We did P3, I believe, right? That was the vector space of all polynomials degree 3 or less under standard polynomial addition scalar multiplication. Right, so you also have M sub Mn, vector space of all n by n matrices. Obviously Rn, you know that one. R sub n, you know that one. We went over those as well. There's also the vector space of continuous functions over an interval. Because that notation I'm going to expect you to know. And on the exam, I may put something like that up there. And if you have no idea what M22 is, you're screwed. Right? So you may want to list out all the different vector spaces we've gone over. So we're dealing with vector space of 2 by 2 matrices. We're defining a mapping from M22 into M22 as f of a times m plus m times a. We will show that this defines a linear transformation. AM and MA, are they the same? No, they're not. Not necessarily, right? They could be. And if I'm not mistaken, there's only one situation where they would be the same. And that's if they're inverses. But outside of that, remember, matrix multiplication, not commutative. Order does matter. But the good news is we're strictly in M22, right? That means A is going to be 2 by 2, M is going to be 2 by 2. What's 2 by 2 times 2 by 2? What's the size? Then A times N, or I think I just did I do N times A? A times N. Still 2 by 2, 2 by 2. So even though AM and MA are not the same, they are the same size. So at least the addition is defined. That's a good start. If that addition wasn't defined, you can stop right there. That can't be a transformation because it's undefined. So there's a good start. Generally speaking, it's good to always just restate your hypothesis. So we're going to choose two arbitrary matrices from M22. And let's choose two arbitrary real numbers, alpha and beta. Obviously, that means I'm going to be going the root of the conjecture to show that this is a linear transformation.
On a quiz or exam, are we going to be forced to use a conjecture or
No,
do something? It's all.
You can do the two properties as well. Like I did here, I noticed that the alpha is going to be kind of hairy here. If I tried using conjecture, I did the two properties separately. Doesn't matter. They're interchangeable.
Okay.
So it's whatever you feel like doing. And there's no time where I force you to use one method. I don't tell you, use the definition to do this or use the conjecture. You can just use whatever method you want. And this will probably be the hardest exam too. It's got all the vector space stuff on it, right? So that's the most abstract exam of the semester.
So the class average will be below 44.
So we'll say 44 out of 50?
100.
No, I hope not. But this is going to be the hardest exam. It's going to be the most abstract. I thought algebra was easy. But yeah, I wrote it, so. So I'm just stating here what we want to show. Right? Sometimes you do that in proof, sometimes you don't. I'm doing it so that I don't have to restate the conclusion. So ultimately now what I can do is I can go, okay, well once I reach that conclusion, I'm done with stop. Well, alpha A plus beta B. That's a matrix in M22, right? Because A and B are from M22, and it's closed under addition and multiplication. So that whole thing is a matrix in M22. What was the rule? Was make your image, your pre-image times n plus n times your pre-image. Now think way back to day number 2, January 23rd, I believe that was. And your properties of matrices. Matrix multiplications distributes from the left, which is that second one, and distributes from the right, which is the first one. So that first grouping would be alpha A, remember that's one matrix, times n, plus beta B, that's a matrix, times n. That second grouping would be m times alpha A, plus m times beta B. Matrix addition. Did we say that's both associative and commutative? Right? So we can just drop the parentheses, because grouping doesn't matter. For scalar multiplication of matrices, if you take a matrix times scalar multiple of another matrix, does it matter where that scalar falls? So for those last two up here, right? Can't I move that alpha out in front of the n? Move that beta out in front of the n? Because where you put the scalar doesn't matter. So that's what we're going to do next. We're going to drop the parentheses because grouping doesn't matter, and we're also going to rewrite those last two terms. And we just said that matrix addition is associative, grouping doesn't matter. It's commutative, order doesn't matter. So group your A's together, group your B's together. That first grouping has a common scalar, right? Factor it out. That second grouping has a common scalar. Factor it out. What is this? What is this? Alpha f of a plus beta f of b1. It's a linear transformation. Two vector spaces, V and U. The set V1, V2, Vn defines a basis for V. And we're going to say that U1, U2 through Un are elements in U. We will prove that there exists a unique linear transformation from V into U, such that f of V1 is U1, f of V2 is U2, so on and so forth. So let V be some vector in your vector space V. then we can write that, right? Why? Let me actually be more specific. For unique constants C1 through Cn, why? I thought I saw a hand. I thought I saw your hand. I didn't. Why can I say that there has to be unique constants C1 through Cn, where V is C1 V1 plus C2 V2 plus so on and so forth? Good.
Because it was defined that V1, V2 through Vn is a basis, and
That's a basis. That's a basis. That is the very definition of a basis. Right? Every vector is a unique linear combination of the elements in the basis. Let me use, if I don't use that, I'm actually confusing myself with the notes, so I will use that. Let's say there's our mapping. And so you take vector from V, you plug it into your map. What our mapping says is you first find your coordinates of V. The transformation is C1 times U1 plus C2 times U2 plus so on and so forth. Do we agree that this would be in U? Right, clearly V is in V. Is this a vector in U? Why?
because that's the definition of a basis.
Well, I didn't say this was a basis. I just simply said there are elements in U.
Oh, because it's just a scalar of U, so when it's just U.
But why?
It's closed by scalar multiplication.
Just scalar multiplication?
Addition.
Use a vector space, which means it's closed under addition and multiplication. Since U1, U2, UN are in U, their linear combination has to be in U. So, good, we have the foundation for a mapping. Pre-image is in V, the output is definitely in U. Now we just have to show that that's linear, and we're done. Well, actually, no, I would have to also show that it satisfies this condition, but that's actually very easy to do. So I'm now going to show that this is actually linear. Yeah, and this is a case where it's probably going to be better to do the two separate properties. So what we have to do is determine your coefficients. I think how I want to word it. This way. All right, the A's are the coordinates for your V, the B's the coordinates for V prime. Right, then V plus V prime, you can just group your V1s together, you get A1 plus B1, V2s would be A2 plus B2, so on and so forth. So this is what we get. Really slow now, that's not good. You can group the A's together, the B's together, right? Because you can distribute, and it's associative. And that gives us f of v plus f of v prime. Shouldn't be too difficult to see the similarities. You're going to get f of alpha v is alpha f of v, so that's a linear transformation. And then it's really straightforward. If you look, based on how we defined it, V1, your C1 will be a number and everything else will be 0, right? V2, C2 will be 1 actually, right? It'll be 1, and then everything else is 0, which from that transformation you can see f of V1 would just be 1 times U1 plus 0. 0 plus 1 times U2 plus 0, so on and so forth. That would satisfy this. Very easy to see. To prove it's unique, you just say, okay, let there be some other linear transformation that satisfies these, and you find that they're actually the same. Fortunately, I don't have time to go through that. Don't forget, your exam is Thursday. So come in prepared. The exam covers everything since exam 1 through today. See you then.
Oh,